In Lesson 1-2, we're going to be talking about properties of real numbers. Our objectives are to classify, graph, and order real numbers, and then we're also going to learn how to identify properties of real numbers. Before we get into our real numbers and properties of real numbers, let's start with some vocabulary that you're going to see. Let's discuss the term opposite, or its mathematical term, the additive inverse. Well, if you have a number A, then we say that its opposite, or its additive inverse, is negative A. If we look at reciprocal, which is a term you should already be familiar with, or the mathematical term for that is the multiplicative inverse, if you have the number A, the reciprocal is 1 over A, but we do need to put a restriction on that because A can't be 0, because if it was, you would have 1 divided by 0, and we are not allowed to divide by 0. So 0 would be the only number that doesn't have a reciprocal. The next thing we're going to look at is the real number system. The first thing we need to realize is we're going to set this up graphically so that we can visualize what's happening here. Everything included inside of this big rectangle is actually the real numbers. Now, there are numbers that are not real numbers, and we call those imaginary numbers, and we'll talk about those briefly in a moment. But everything inside of that big rectangle is the real numbers. Now, the real numbers are divided up into two parts. You have rational numbers. So when I divide this, I now have two parts. You have rational numbers, and then you have what we call irrational numbers. The rationals are then broken up into smaller sections, and I'm actually going to start and work my way from the inside out. So, the innermost rectangle here is called the naturals, or the natural numbers or counting numbers. Okay. Our next rectangle is called the whole numbers. And then the last rectangle inside of our rational numbers here is called the integers. So now let's take some time to discuss what those sets of numbers are. So again, working from the inside out, because that's the most exclusive of the numbers. The natural numbers, or we said those are the counting numbers, are the numbers 1, 2, 3, and so on. Notice there's no fractions or decimals. When you get to whole numbers, the only difference between whole numbers and natural numbers is whole numbers are now allowed to add the number 0. So it's 0, 1, 2, 3, and so on. Now, integers are just the whole numbers with their negatives. So integers would be things like negative 3, negative 2, negative 1, 0, 1, 2, and so on in both directions. Now, once we get to rational, that's where we can start having fractions and decimals. Matter of fact, let's go ahead and talk about a definition of rational numbers. Rational numbers are numbers that can be written as a fraction. So if you can write them as A over B, where B can't be 0, then we call it a rational number. All right. So if I look at a decimal number, something as simple as, let's say, 3.1, that's a rational number because it could be written as 31/10. All right. If I had 4, that would be rational because it could be written as 4 over 1. A repeating decimal, let's say, we'll just pick one we're familiar with, 0.333 repeating. That's rational because it's written as 1/3. So rational numbers, you've probably heard this terminology before, rational numbers are numbers that repeat or terminate. In other words, either it's a repeating decimal or the number just stops, like 3.1. It's 3.1. There's nothing after the 1, and it terminates there. Now, irrational numbers are numbers by definition that are just not rational, so they can't be written in fraction form. But an easy way to remember an irrational number, you're familiar with some already. Pi is irrational because it goes on forever and never stops and it never repeats. Radicals that are not perfect squares. The square root of 2 is irrational. The square root of 15 would be irrational. Now, the square root of 16 would be rational because that's 4. Another irrational number that we're going to look at later in this course would be e. E is actually used to symbolize a number. It's not a variable in this case. It's the number e, and it's approximately 2.7, and it goes on, but it never stops or repeats. It's like pi, which we know is 3.14, and then go on. So if you're looking for irrational numbers, they either have to have pi, e, or be a radical that doesn't simplify to a perfect square. Now let's take a moment to classify and graph the following numbers on the number line. So let's look at our numbers. First of all, the number 3. By looking at our sets of numbers, we know that 3 is a natural number, it is a whole number, it is an integer, and it is a rational number. Now if we graph that, then we're just going to come over here to where 3 would be on the number line and put a dot. We'll label that as 3. Now, negative 2.5, since that's a decimal, then that would be just a rational number. So negative 2.5 would be over here between negative 2 and negative 3. So we'll put a dot here, and that'll be negative 2.5. 17/5, well, if I take 17 and divide it by 5, I'm going to get 3 2/5, but 2/5 is 0.4, so that's going to be 3.4. Well, 3.4 is between 3 and 4, but not all the way to 3.5, so a little bit less than 3.5. So we'll label that as 3.4. Now, as far as classifying that number, since it is 3.4, it's a decimal number, it would be rational. The square root of 23, well, we could use our calculator and come up with the square root of 23, or we could actually just kind of approximate where the square root of 23 would be. So we know the square root of 25 is a perfect square, and it is 5. So the square root of 23 would be a little less than 5. And that's one of the things that I'm going to want you to do is be able to just kind of approximate these numbers. So we'll call that the square root of 23. Now, because that is a radical that does not simplify to a perfect square, then that would be an irrational number. Negative 4/3. Well, again, if I divide that, I get negative 1 1/3, or negative 1.3 repeating. Since that's a repeating decimal, we know that that is a rational number. So 1 1/3 would be just a little bit past 1. So there's going to be negative 4/3. And then our last one is the absolute value of negative 5. Well, we need to recall what absolute values do. Remember that absolute value takes a number and tells the distance it is from 0. So the absolute value of negative 5 would be positive 5. So we come over here and we'll put a dot at 5. And that's the absolute value of negative 5. Since that number simplifies to 5, then that's going to make it a natural number, which makes it a whole number, which makes it an integer, and a rational. Now the last thing we're going to do is just look at properties and discuss them. This is just one of those things that you're going to have to memorize. If you understand where the terminology comes from, it makes it a little easier to memorize what the terms mean. So first thing, let's look at this property called closure. Here's all that closure means. And notice that we have two columns here, a property for addition and one for multiplication. But if you understand the general concept of the property, you'll know how to get the addition and multiplication properties for those. So closure just says this: if you start with two types of numbers and you add them and you get that same type of number, then we say that that is closed by addition or under addition. We also do the same thing with multiplication. So example, if you have two real numbers and then you multiply them or add them, your answer is real number. So then we say that the reals are closed under addition and multiplication. All right, let's look at our next property, which is the commutative property. Now, the commutative property comes from the term commute, which means to move things around. So notice that that's what we're saying, that if you add numbers, you're allowed to change the order and get the same answer. And the same thing is true for multiplying. And you know that if you add 2 plus 7, you get the same thing as 7 plus 2. Or 3 times 5 is the same thing as 5 times 3. The associative property has to do with the term associate, which is groups. And it just says you're allowed to change groupings for adding and multiplication. So if you have A plus B grouped together and added to C, then you could add B plus C and add it to A and get the same answer. So you can change the parentheses. Now the big thing on associative property is notice the order didn't change. Your letters went A, B, C, and then on the other side of the equation they're A, B, C. So it's still the same order. Same thing for multiplication. We have A, B, C, A, B, C. What we've done is change where our parentheses were. Now the identity is the property that gives you back what you start with. Okay, so think about that as like a mirror where you do something, you perform an operation, and you get back what you started with, like seeing a mirror reflection of yourself. So if you have A and you add 0, then you get A. Or 0 plus A is A. We'd say 0 is the additive identity because that's what you can add or what operation you can perform and get back what you start. All right, and then same thing with the multiplicative identity, except it's 1. What can I multiply by and give me back what I started with? Well, A times 1 would be A, and 1 times A would be A. So we would say 1 is the multiplicative identity because that's the operation that I can perform or the number I can use to give me back what I started with. The next property is the inverse property, and we've already discussed that terminology in our vocabulary. We say that negative A is the additive inverse or the opposite of A if A plus negative A is 0. So the inverse is where you want to get back, in this case, 0. What undoes that property or that number? Okay? And then in multiplication, you have A times 1 over A is 1. So we would say that 1 over A is the multiplicative inverse or the reciprocal of A. And then the last property is the distributive property, and you've used that before. It just says that if you do A times B plus C, you get A times B plus A times C. And technically the name is the distributive property of multiplication over addition because that's what you're doing, is you're taking multiplication and applying it to an addition problem. So you're distributing the multiplication over the addition problem.